Awesome. Thanks, Aaron. Let's go ahead and dive in here. So, topic of discussion here for this fire talk is defending serverless infrastructure. So, overall, with the research project that myself and a colleague of mine, Brandon Evans, put together, we wanted to expand on some pre-existing research that there's obviously a lot of content out there for AWS, not so much on the Azure and GCP side. So answering the same questions that had been covered before, we wanted to look, where is the source code at? How do we find secrets? How can you exfiltrate authentication tokens? Potentially look into some of the blue team and incident response controls, such as detecting stolen auth tokens, maybe looking at network controls for flow logging, trying to figure out if we can look at those audit logs and maybe monitor and detect some of this activity in the other cloud providers. So without getting too far ahead of myself, I need to give some shout outs to folks that maybe inspired some of our ideas. Gal Bashan originally I remember years ago reading the blog post that he posted on Lambda internals, where it was just a function that gives you command and control so you can inspect the environment and try to figure out, where am I? Where is this code executing at? Some great contributions from PureSec and Pertigo on the serverless top 10. That's also a really good resource for defending your serverless infrastructure. Also, Scott Piper and some of the folks at Rhino Security have had some good commentary, whether on Twitter or in the pen testing with Callie book. So all of these combined together to kind of pique my interest in serverless and really try to explore more than just AWS. So building on Gal's research with the Lambda internals, what myself and Brandon Evans put together is an open source project that's out in my Puma Security repository called Serverless Pray. And the whole idea of this project is automated infrastructure. So there's some Terraform code, there is some serverless framework code sitting there, some YAML configs that allow you to launch a Google function, an Azure function, and an AWS function that are all vulnerable to command and control vulnerabilities. So it's all out there in that GitHub link that's on the slide. There's also a YouTube link to a full 60-minute version of this talk that has a lot more detail in terms of the commands that are buried in the docs on that repo. So you can check that out and get some more details on some of the high-level things that I'll show you here during this more rapid discussion. So in the beginning of the research, we've got command and control. What are we actually looking for? What does the function execution look like? So I'll bounce around a little bit here in some of these demos. Ultimately, what I wanted to do is get command and control and figure out what OS am I running on. So you're seeing me standing up a Netcat port on an EC2 instance. I'm invoking the GCP function, establishing command and control back. So the first question who am I, right? Google apparently runs their functions as root, which I thought was really interesting. And then we can pop in here, what OS am I on? So for the record, this is a Go function. It might change per platform, but the Go function's running in Ubuntu 18.04. And we'll go on and look for where am I? So I'm in SRV files. Okay, oh, perfect. We are defaulting into the source code directory. There's a YAML file. And this kind of goes into, if I've got command and control, it's this simple to inspect the environment. And eventually I'll just cat out the YAML file and find, some secrets in this little config file. So all of that is set up in each of these functions. And the documentation we put together compares what all these things are doing. So in AWS, we ran a Node 12 function. That's on Amazon Linux 2. Your default directory is var task. In Azure, we spun up a .NET Core function. So that's on a Debian instance. You default to the home directory, which I thought was interesting. Both of those are running as non-root users. And then you've got the Google example that I just showed you, which was a Go 1.11 function on Ubuntu, SRV files, running as root. So if you're doing a benchmark compare right there, I'd say Google is most likely the weakest item because, well, they're running as the root user inside the function. So that was something interesting I saw in that research. The next question, where's the source code? So here's your benchmark. Here's where we dug up and found all the source code. Nothing really special about this. Lambdas is in var task. Azure functions, there's a little bit of IIS showing here, even though it's on a Linux box. It's in the home site www root directory. And then in GCP again, SRV files. So there's a real high-level snapshot of these serverless environments and where things are actually living for you to start attacking the functions. Your next pivot, find the environment variables. So in each environment, we catted out proc self environ, and we looked at what resources are available. Now, it's pretty common knowledge at this point that AWS stores their actual access keys for the execution role in their environment variables. So in this example, I wanted to take a look at what was in Azure's. Azure's arguably has more interesting things in it than AWS does, because there's a lot of different keys in here for different items that the function is interacting with. So you've got a connection string to an Azure storage blob that's hosting the source code. So from the function, you can actually get back to the origin that the code was sideloaded from, which I thought was interesting. You've also got some encryption keys that are used to decrypt the incoming authentication token in order to invoke the function by default. And then there's the MSI secret, which is a nice little random identifier that you can use to inspect the managed service identity endpoint. So I'll show you that example here in a few minutes. So let's look at that execution role. So we'll switch from GCP to Azure for this demo. So let's go to Azure and we'll stand up that same netcat connection, except this time I'll invoke the Azure function. Once we've got our connection, we can take a look at this MSI endpoint. So what you're going to see me run is a curl command that grabs from the MSI endpoint, which is one environment variable, and uses the MSI secret header with the other random variable. You'll notice now I've got an access token. This access token is synonymous on the AWS side as the access keys that are tied to the execution role. Except the major difference here is that this access token is a JSON web token, and it is scoped, if you look at the actual JSON web token on the screen, to one service. So if you were going to try to pivot around this cloud environment, you would actually need a token for storage, a token for Vault, and a token for any of the other services you want to interact with. So it's actually a fairly decent setup, assuming the attacker can't just arbitrarily make tons and tons of requests into that function. But it is scoped, which is stronger than the AWS and GCP equivalents. So at this point, I'm using the JWT to authenticate directly into the storage service and eventually from an outside world using the token to exfiltrate a little image from a private storage account that's only accessible to the serverless function itself. So you can see here we use that token and we pulled the image down from the storage bucket. So once you steal the creds out of MSI, you can essentially masquerade around as the function itself. In our research, we found this is the same across all three clouds. Amazon has an execution role attached to a Lambda function. Azure has a managed identity, which I just showed you, attached to the execution role. They call it their managed identity. And then GCP uses service accounts to authenticate to backend GCP resources. One thing that I just have to mention is that Azure and AWS follow a more least privileged model with their functions. So you spin up a Lambda or you spin up an Azure function, by default, you've got very little rights to other services such as logging or such as storage or such as the vault. I'm sure Kat Traxler in her GCP talk earlier today probably pointed this out to you. So if you've been around all day, you know this. If you're late, I'll reiterate it. In GCP, if you stand up a function and you do nothing in terms of defining permissions, you are opted into an editor role inside of this project, which gives you full read and modify permissions on existing resources. It's actually nuts how permissive this role is. So if you have one takeaway from the GCP discussion, it is define your own service accounts and define nice locked down policies for that service account before you spin up a function. Credential storage. So where are the creds? We just talked through the Azure version of this, which is managed identities. So that is in a very special dynamic endpoint inside of the functions execution environment. Environment variables is where Lambdas have always looked for those. So those are very easy to get to if you just have something like a local file inclusion vulnerability. Compare that to Azure's, where you actually need to dump environment variables and you need command injection to inject a custom header and invoke a random endpoint that's also in the env. So Azure's is by far the strongest authentication mechanism, or I guess strongest in terms of preventing me from stealing the creds. Google, somewhere in the middle. Theirs is in the standard instance metadata service. So you've got a curl 169.254, 169.254, same as the virtual machines. And you have to inject the custom metadata Google header to get to the credentials out in GCP. We also looked at persistence and exfiltration. So in terms of these credentials lifetime, how long do you have to exfiltrate creds from, or how long do you have to use the creds after you exfiltrate them from the environment? So Lambdas is not documented very well, probably to no one's surprise. If you look at some of Amazon's docs in the internal space, they maybe don't tell you quite everything that's going on. So what I did is I ran a little watch script and I just tried to use the credentials, every 10 minutes for a series of hours. And where it landed is that the Lambda credentials that you steal are valid for around 12 hours, which is really interesting from a serverless perspective. If you've got a really privileged cloud custodian function, for example, that's able to blow away and correct resources, and somebody compromises that function, do you really want those credentials to live that long? You can't control this. This is just a default in the platform. It is what it is. Azure is a little bit less. You're looking at about 8 hours for that JWT. That's at least really well documented because, well, the JWT has the expiration time in it, so you can just look. GCP is by far the most strict. 30 minutes and your OAuth bearer token is dead. So GCP's rotates by far the most frequently. We also wrote some malware to the environment. So let's put some malware in the serverless environment. And this is kind of testing warm and cold starts a little bit. So how long does the execution environment stick around before it's recycled and it comes back fresh? Lambdas, again, about 11 minutes or so, where we could actually use our command and control to drop in, check the malware file, and it lives for about 11 minutes. Azure's is 6, GCP's is about 3 minutes before that malware disappears. So that's what you're looking at from a by default persistence perspective. Worth noting that AWS very recently just allowed you to integrate Lambda functions with more persisted storage into EFS, which the first thought to my mind was, oh, perfect. If there's a mounted EFS volume, well, now we've got permanent persistence for malware and it can live forever. So that's another feature that came up that is kind of interesting. Digging into the detecting compromised credentials, so more the blue team approach, we really looked at audit logs first. So you've got audit logging through CloudTrail, Azure Monitor, and IAM Audit in all three clouds. AWS's is by far the easiest to turn on. So you've got a trail and it captures everything. GCP's is probably second in my list, where you have to actually enable IAM audit logs per service. So if you want them from the secrets manager, you need to go turn that on. But you need to also go to do that for storage and any other downstream services you're going to use. Azure's, I'm going to rank third here because it works for some services, but not so well for other ones. So Azure Monitor worked great for the Key Vault. I had a diagnostic waiting there in Security Center saying, turn this on. So I did, but then I tried to do it in Azure Storage and no data actually ever showed up to show a compromised credential. So that's a hole there. There's an open ticket. They're working on it. Supposed to be done at the end of Q2, which, well, we're getting to that point, right? And I have not seen it be resolved yet. So Azure's is just kind of inconsistent, in my opinion, across how things are working. Storage is their oldest platform, so it kind of makes sense. They just haven't quite got it up to speed with the modern way to do it. We looked at network access control as well. So from a network access control perspective, here's your default. Your function has full out egress to the outside world. And in order to talk to the other cloud services, storage, secrets, which are both in the functions, you're going to get to the outside world. And there's really no logging or flow logging or telemetry on any of these connections. So think command and control. There's zero evidence of what our functions are doing for you to look at. So what you've got to do is look at their network integration options. I'll say right here, Amazon by far the most mature product here, because you can throw a Lambda into a network in a VPC, attach a network interface to it, and take advantage of flow logging, traffic mirroring, egress security groups, and internal endpoints. I turned it on in Azure, and the first thing it told me was, oh, you need to upgrade to a premium plan. Oh, that's fun, right? So I basically turned a serverless ephemeral environment now into a 100% up all the time running web server that just happens to have a function on it. When you do that, you can get into the networking section. GCP has a serverless VPC access feature, but it's not putting your function in a network. It's allowing your function to talk to a VPC. You don't actually get a lot of the controls that you get out in the AWS world. So in the final video, here's what we'll do. I'll run it for exactly 2 minutes, and we'll take a look at some of the controls that AWS offers if you turn on your VPC connectivity, set up egress filters, and then set up some of those private endpoints. So let's go ahead and kick this off. I'll let it run here for a little bit. So now I'm picking on AWS. We're trying to stand up a connection on port 1042, but I have an egress rule that's preventing the function from talking out through a security group on that port. So you can see on 1042, we're getting nothing. So that's a good thing. We're restricting traffic from an egress perspective, but smart attackers that, realize almost every single environment in the world is going to allow traffic on port 443 are just going to change their port over. So the good news about being blocked here on port 1042 is now that I've got network integration, I can actually query the flow log data for this. So from a blue team perspective, I'm just running a quick little CloudWatch query, and we'll see when the results come back, hey, there's my flow log. I'll scroll up a little bit, and you can see the reject packet here on the functions network interface heading out to my 3.12 IP on port 1042. So that's a good thing. So because we've got the function integration into a VPC, we're getting some more network forensics analysis. So let's stand up our command and control port here on 443. You'll see that this is actually going to go through now because we've got egress on 443 allowed. And this time, the connection works. So we've kind of bypassed the egress rule. What I will do real quick, if we've got a minute, is we're going to extract these access keys. And what we'll do is test the actual endpoint policy that I've got in place. So I've got a policy right on. So we'll keep rocking here. I've got an endpoint policy in place on a bucket now, leveraging the VPC endpoints that stop external requests outside of this VPC from accessing the bucket. So this function feature is actually now preventing the damage from stolen creds. So in the environment, I'm just setting up my 3 environment variables real quick. Notice we run the S3 sync call that worked previously, but it's access denied because the bucket policy says you have to be inside of this VPC. So what I'm doing, the final section here is, again, we've got audit logs now. So we're looking with an Athena query at the CloudTrail logs, looking for execution commands made with the execution role for this function. So we'll run this command real quick to check the audit logs, and we'll see now we've blocked egress traffic, we've stolen creds, we've attempted to exfiltrate, and we've got an access denied log entry from CloudTrail. So from the blue team perspective, it always comes back to network controls, right? The Lambda functions are able to do that. So for that, I will go ahead and hang it up here. That's the end of the defending serverless discussion. I'll pass it back to Aaron, and you can kind of facilitate the Q&A stuff here for a minute.
Couple questions about networking. And so Andres asks, VPC service controls is not enabled by default. So have you had a chance to test any of these scenarios in GCP with VPC service controls turned on? Would that have prevented the Cloud Functions API from accessing the internet?
I literally found out about VP service controls within the last 2 weeks. And when I read about it, I got really excited, thinking that is the first time where maybe we could use that. The one thing I didn't realize, you have to have, I believe, organizations set up in order to set VPC service controls up to apply those constraints. But if I circle back to this project, that's the next thing I'm going to try, because it sounds exactly like what I was looking for to apply that policy.
And absent that, just to confirm, all of these systems by default have access to the internet, and there's very little way to
100% correct. Yeah. Every function by default, full egress, 0 monitoring and logging from the network side.
Are you aware of any public incidents where serverless functions have been compromised, or any specific malware or rootkits that target the serverless environment?
That's a great question. I have not seen like an in the news company announcement saying like we got breached through a serverless function. Has it happened? Probably, but no one is really talking about that right now. So I have not seen anything. Obviously, most of the metadata attacks that we've seen in the news are coming through like virtual machines, and some of those public breaches. But it's important to realize the serverless functions are vulnerable to the same sort of attack. It's probably just less common, right?
Cool. And then I guess a question on logging, which is like, do you have a wish list for audit and forensic logging for serverless? Anything that you would recommend for detecting data exfiltration or other sorts of patterns to see whether this happened?
Yeah, so we went through the IAM audit logs, CloudTrail. We also looked at NetFlow, which those are things network folks can get behind normally. But my wish list, to be completely honest, and it's really hard to get it, is to get the development staff, the engineers writing the functions themselves, to put actual audit log statements in there saying, hey, function is reading from secret, and give you some of that application level telemetry. That's usually what's missing from all systems. Serverless is no different, but that's going to be really high on my list because it lives for 200 milliseconds. So that's all you've got when it's said and done.
Well, very cool, and certainly no shortage of serverless usage in our environment increasing. So excited to see those attacks and start thinking about how to defend against them. So we'll be back in 5 minutes with our closer talk, which is Ian Mackay, talking about the AWS account controller. It's going to be a really fun closer, so I'm looking forward to it. Thank you so much, Eric.
You're welcome. Thanks for having me, fellas.